welcome to the Deep Dive. Today we are peering into, well, the microscopic world of silicon deadlines, these really non-negotiable fundamental rules that govern whether your sophisticated digital system actually works perfectly or crashes unpredictably.
Yeah, exactly.
We are diving deep into field programmable gate arrays, FPGAs, to try and master timing violations, what some people call the silent killers of hardware reliability.
And that's really where we live today, isn't it? Right at that intersection of speed and stability. So our mission for you, the listener, is to move beyond just, seeing negative Slack pop up in some timing report.
Right, that dreaded red text.
Exactly. We're aiming for genuine mastery here. And that means really understanding the physical timing demands of the simplest sequential element, the flip-flop.
The building block.
The absolute building block. And then walking through the rigorous, and I mean really quite pessimistic mathematical methodology, static timing analysis, or STA, that's what guarantees stability across this massive range of operating variability we call the PVT corners.
PVT, process, voltage, and temperature. We'll definitely get into that.
Oh, yeah.
And we've got a pretty comprehensive set of sources for this deep dive. We're analyzing materials, covering sequential timing fundamentals, the physics of metastability, which often seems a bit mysterious.
It can be, yeah.
Detailed STA methods, like the ones used in toolchains like Vivado, and some advanced industry-standard ways to fix things, notably that iterative ultrafast methodology.
That's a big one.
Yeah. So this isn't just about, scraping by and closing timing. It's about building robustness into your design from the ground up. Okay, let's unpack this and get right to the foundation of why digital things sometimes fail. Okay, so at the absolute core of every synchronous design, it's the sequential element, usually that D-type flip-flop. We rely on it completely, right?
Totally. It's the memory.
And its ability to correctly capture data relies 100% on satisfying two intrinsic fixed timing parameters. These define a critical stability window right around the active clock edge.
And these parameters, this is really key, as you said, they're physically baked into the silicon by the foundry when the chip is made. You can't change them. They are truly non-negotiable.
Like the laws of physics for that specific chip.
Pretty much. You can think of that clock edge like a super high-speed camera shutter trying to snap a picture of something moving really fast.
Okay.
If the data, the subject, is still moving or blurry right when that shutter fires, well, the photo's ruined.
You get garbage.
You get garbage. The flip-flop's internal structure, it needs absolute stillness, data stability for a tiny defined period both immediately before and immediately after that clock event.
Okay, let's define that first period, setup time, or we see it written as TSU. What exactly is that?
So TSU is the minimum amount of time the data signal at the input pin has to be stable, meaning perfectly still, not changing, before the active clock edge actually arrives.
Before the snapshot.
Exactly. If the data transitions, or maybe it's still settling from a previous change during this little preparatory phase, the tool flags a setup violation. Basically, the internal transistors haven't had enough time to sort of precondition themselves to recognize and then latch the incoming value before the latch now command arrives from the clock.
Okay, so data needs to be ready early. What about after the clock edge?
Right, so immediately following that clock edge, we hit the second, and just as crucial, deadline, hold time, or tend to wait.
This is the minimum amount of time the data has to remain perfectly stable after the active clock edge has already passed. Think of it like the internal latching mechanism inside the flip-flop takes the tiny fixed amount of physical time to actually lock in the value it just captured.
It needs a moment to grab hold.
Precisely. So if the input data changes too quickly, if it vanishes or transitions too soon after the edge, that internal lock fails, and that's a hold violation. So we've got this razor-thin window. You need stability TH before the clock and stability TAs after the clock. If you violate either of those, what's the big, scary consequence?
The big one. It's the dreaded metastability. And this is really important. It's not just a logical error like a bug in your code. It's a failure of physics within the digital circuit itself.
Physics failure. Wow.
Yeah. Violating either TSU or AT-base basically throws the flip-flop into this unstable equilibrium. The internal switching nodes, the points inside that should quickly snap to either VDD for a logic 1 or ground for a logic cello.
The binary states.
Right. Instead, they get stuck. They land at some intermediate indeterminate voltage level. They're literally stuck halfway between 0 and 1.
That sounds fundamentally wrong for digital logic. What happens then? How does it behave?
Well, the output becomes completely unpredictable. It might oscillate bounce rapidly between high and low for a bit, Or, and this is often worse, it can take an arbitrarily long time to finally make up its mind and resolve to a stable 0 or 1.
Arbitrarily long. Like, you could take ages.
Potentially, yes. And that's the real danger. If that resolution, the time the circuit needs to sort itself out, actually exceeds the clock period of your system,
Oh.
then that failure just propagates. It ripples through the downstream logic, corrupting data flow, and yeah, it can potentially crash the entire system. Once a circuit goes metastable, you're just waiting for it to resolve. And how long that takes is statistical, often talked about in terms of mean time between failures or MTBF.
Okay, so that's the scary outcome. When we look for the sources of these violations, where does this instability most often creep in? Our sources are pretty clear on this one.
Yeah, the number one culprit, far and away, is dealing with asynchronous signals, usually referred to as clock domain crossings or CDC.
CDC,
Right.
signals coming from outside the FPGA or maybe different clock zones inside.
Exactly. It's unavoidable in any real-world system. If a signal comes from, say, another chip on the board or from a part of the FPGA running on a totally independent clock, well, that signal's transition can happen at any possible time relative to the clock trying to capture it.
There's no coordination.
None at all. So, just by pure probability, eventually one of those random transitions is going to land precisely within that critical TSU or 12 allele window. If you tried to directly sample an asynchronous signal without some really robust synchronization logic, well, you're basically designing for eventual statistical failure. It will happen.
So the standard defense against this statistical certainty is the synchronization chain, right? Sticking a couple of flip-flops back to back.
Yep. Usually a cascade of 2, sometimes 3 flip-flops.
Why 2 or more? What's the logic there?
Okay, so the first flip-flop in the chain, let's call it FF1, is the one directly connected to the asynchronous input. It's the one that might go metastable.
The sacrificial lamb.
Kind of, yeah.
Yep.
So if FF1 does go metastable, the second flip-flop, FF2, is clocked by the same destination clock, but it's sampling the output of FF1. This gives the potentially unstable output of FF1 one full clock cycle, the entire period, to hopefully resolve itself into a stable 0 or 1 before FF2 tries to capture it.
Buying time for it to settle down.
Exactly, buying resolution time. And you often see 3 flip-flops used in really high reliability designs like industrial or automotive. FF1 is susceptible, FF2 provides the resolution cycle, and FF3 adds another cycle just for extra stability guarantee. It pushes the MTBF way, way up.
Okay. And related to this, sometimes you hear about metastability hardened flip-flops. Now wait, if metastability is this fundamental physics thing, how can you harden a flip-flop against it?
That's a really good question, and the wording is important. They do not eliminate the possibility of entering the metastable state. That's impossible.
Okay.
What they do have is specialized, usually faster, internal circuitry. This circuitry is designed to accelerate the recovery time, meaning the time it takes for that indeterminate voltage level to finally snap to a valid 0 or 1.
So they get out of the unstable state faster.
Much faster, usually. By shortening that potential resolution time, they dramatically increase the MTBF, sometimes by orders of magnitude. But think of them as tools to manage the risks much more effectively, not tools that eliminate the fundamental physical problem.
Got it. Okay, so beyond these chaotic external signals, another big source of failure is more internal, maybe human error. Specifically, getting the timing constraints wrong.
Oh, absolutely critical. It's like trying to navigate without a map or maybe with a really bad map. The optimization tools, synthesis, placement, routing, they are guided almost entirely by the design constraints you provide, typically in an SDC or XDC file. Synopsys design constraints, J-Link's design constraints.
SDC, yeah.
If those constraints are missing or if they're inaccurate or just incomplete, the tools basically shrug their shoulders about timing. They'll default to optimizing for something else, maybe minimizing chip area or reducing power consumption.
Which might be the opposite of what you need for speed.
Often, yes. And this leads to really suboptimal placement. For example, 2 registers that are supposed to talk to each other really fast might end up placed physically miles apart on the silicon die.
Creating a huge delay.
Exactly. A long, slow route that's highly susceptible to variations and timing errors. Good constraints force the tools to prioritize minimizing path delays for critical signals above almost everything else.
Okay. And finally, underpinning all these calculations, all these delays, is the physical environment itself, which isn't constant. We need to talk about the crucial impact of PVT corners. Process, voltage, temperature.
This is absolutely fundamental to why static timing analysis has to be so conservative, so pessimistic. The delay through any logic gate or any wire on the chip is not a single fixed number. It varies, sometimes wildly, based on these three things.
Okay, break it down. How does PVT affect setup checks, the data arriving too late problem?
Right, setup is a max delay problem. So to ensure our design works even when everything is conspiring to make signals slow, STA must analyze the critical paths against the slow conditions. This means assuming the lowest possible operating voltage, low V, the highest possible chip junction temperature, high T things get sluggish when hot, and assuming the chip came from the slowest end of the manufacturing process variation spectrum, the slow process corner.
So worst case, everything for being slow.
Exactly. These three conditions together maximize all the gate delays and all the routing delays. This gives you the absolute worst case scenario for data arriving late. If you pass setup timing under these conditions, you should be good.
Okay, that covers late data. What about the opposite problem, hold checks? Data arriving too early or changing too fast?
For hold checks, which are a minimum delay problem, STA has to flip everything and evaluate against the exact opposite, the fast conditions.
High voltage, low temp.
Precisely. High operating voltage, high V, low junction temperature, low T things speed up when cold, and assuming the chip came from the fastest possible end of the silicon process variation, the fast process corner. These conditions minimize all the delays.
So if the data doesn't change too quickly, even under these super fast conditions,
Then you've guaranteed robustness against hold violations across the entire operating range. This necessity for comprehensive pessimistic modeling across the full PVT envelope is really the bedrock of reliable high-volume FPGA design. You have to cover the extremes.
all right, so we understand the physical deadlines, TSU and total LD, and we know the environment varies a lot with PVT. Now we need the tool that actually checks everything. Let's properly introduce static timing analysis, STA. Why do we rely on STA instead of just, running a simulation with lots of test cases?
Well, STA provides coverage guarantees that dynamic simulation just can't realistically match. Think about dynamic simulation. You need exhaustive input vectors. You'd have to somehow apply every possible combination of inputs across all possible internal states to be truly sure about timing. That's usually computationally impossible for complex designs.
Right, the state space is enormous.
Exactly. STA, on the other hand, it works differently. It's mathematical. It traces every single possible timing path through the synthesized netlist. We're talking millions, sometimes billions of paths.
Legit, single one.
Every single one. And it uses those pessimistic PVT delay models we just talked about. So it can confirm timing closure or identify failures for every path in the design without ever needing to run a single functional test vector. It's analyzing the structure and the timing models directly.
Okay. Can you break down the structure of a timing path that STA looks at? What are the components?
Sure, it's pretty logical. A timing path always starts at a start point. This is usually either an external input pin of the FPGA or it's the clock pin, CK, of a sequential element, like the flip-flop that's launching the data.
Well, launch flop. Okay.
Then the signal travels through the combinational logic network. This is all the stuff in between the lookup tables, LUTs, the adders, multipliers, multiplexers, and all the wires, the routing resources that connect them. Basically all the logic that processes the data.
The thinking part.
The thinking part, yeah. And finally, the signal arrives at the endpoint. This is either an external output pin of the FPGA or it's the data input pin, the D pin, of the sequential element that's supposed to capture the data.
The capture flop.
Right. So start point, combo logic, endpoint. STA calculates the total time it takes for the data signal to make that entire journey.
And that calculation gives us the main metric we always look at in the reports.
Yeah.
Slack. What is slack exactly?
Slack is simply the timing margin. It's the difference between when the data is required to arrive at the endpoint and when it actually arrives based on the STA calculation.
Required versus actual.
Exactly. We always want the actual arrival time, TR, to be less than or equal to the required time, TREQ. So the calculation is slack, TRQ, TRE.
Okay.
If that number is positive, you have positive slack. That's good. It means you have timing margin, you met the deadline with time to spare. If the number is negative, you have negative slack. It's a timing violation. You missed the deadline.
And the amount of negative slack tells you how badly you missed it.
Precisely. If you have negative 0.5 nanoseconds of slack, it means your data arrived half a nanosecond too late for setup, or changed half a nanosecond too early for hold. It tells the optimization tools how much delay they need to somehow shave off that path, or it tells you how much you might need to slow down your clock.
Okay, let's nail down that fundamental difference again between setup and hold checks.
Yeah.
Because you said this is really critical for figuring out how to fix things.
Absolutely critical. Let's reiterate. Setup failures are max delay problems. They happen because the data path is too slow. The crucial point is they are entirely limited by the clock period, TCLK.
Operating frequency.
Right. If your data arrival time is greater than your clock period, adjusted for clock skew and setup time, you fail setup. The fix, at least mathematically, is straightforward. Increase TCLK. That means reducing your operating frequency, slow the clock down.
Give the slow data more time to get there. So setup failure is basically a throughput problem, often fixable by sacrificing speed.
You got it. Now, hold failures. They are completely different. They are min-delay problems. They happen because a path is too fast or the clock skew works against you.
Too fast. That sounds weird.
It does, but remember THLD. The data has to stay stable after the clock edge. If a new value races through the logic and arrives at the capture flop's D pin before the hold time window for the previous value has expired, you get a hold violation. The critical insight here is hold failures are independent of the clock period.
Independent. So slowing down the clock does nothing.
Absolutely nothing. If you have a hold violation at 200 megahertz, you will still have that exact same hold violation if you slow the clock down to 10 megahertz. It depends only on the physical path delays at the fast corner and the clock skew between the launch and capture flops.
Wow. That makes hold violations seem fundamentally more serious structurally.
They often are, yes. They indicate a basic timing relationship failure that won't just go away by reducing speed. You have to physically alter the path delay or fix the clock skew.
Okay, that brings us neatly to clock skew.
Yeah.
The double-edged sword of clock skew. Define skew for us again.
Skew is simply the difference in arrival time of the same clock edge at two different points in the circuit. Usually we care about the skew between the clock pin of the launch flip-flop and the clock pin of the capture flip-flop.
And it's unavoidable because wires have different lengths.
Exactly. The clock signal has to travel physical distances on the chip, and those distances are rarely identical. So some skew is inevitable. Now, why is it double-edged? Let's consider positive skew.
Okay, positive skew is when?
Positive skew means the clock arrives at the capture flop later than it arrives at the launch flop. So TA nano is greater than the sevel phi MNCA.
How does that affect setup?
It helps setup. Because the capture edge is delayed, it effectively gives the data more time to travel from the launch flop to the capture flop. It borrows time from the next clock cycle, making the current timing path requirement easier to meet.
Sounds great for setup.
It is, but it's potentially disastrous for the hold check.
Ah, the other edge of the sword. Why?
Remember, the hold check happens relative to the launching clock edge. If the capture clock arrives late, positive skew, it drastically compresses the time window available for the data launched by that edge to meet the hold requirement at the capture flop before the capture clock arrives. The data might race through a short path, but the late capture clock means the previous data wasn't held long enough.
Okay, so positive skew helps setup, hurts hold. What about negative skew? Capture clock arrives earlier.
Negative skew does the opposite. It hurts setup because the capture edge arrives sooner, giving the data less time to propagate. But it helps the hold check because the earlier capture edge provides more time after the launch edge for the hold requirement to be met.
So skew is this constant trade-off. Now, if skew can be beneficial sometimes, like positive skew for setup, how do the big FPGA tools like Vivado or Quartus handle this? Do they just use the actual calculated skew?
This gets into the design philosophy of why SDA has to be conservative. The tools know that relying on random, localized routing effects that happen to create beneficial skew is dangerous. That helpful skew might disappear under different PVT conditions, or if the design is placed and routed slightly differently next time.
It's not reliable.
Not reliable enough for robust design. So to guarantee timing across all corners and implementations, SDA tools employ techniques, sometimes bundled under names like Common Path Pessimism Removal, CPPR, but the underlying principle involves deliberately being pessimistic about beneficial skew.
What does CPPR actually do?
Okay, imagine the clock path from the main clock buffer splits. Part goes to the launch flop, part goes to the capture flop. There's usually a shared segment of that path before the split.
Right, a common trunk.
Exactly. Now, when calculating timing, the tool might model that common trunk with slow corner delays for the setup check and fast corner delays for the hold check on both branches. CPPR recognizes this shared path and removes the artificial pessimism caused by applying different delays to the same physical wires in the common segment. It makes the calculations slightly more realistic by only considering the delay differences after the path splits.
Okay, so CPPR removes some pessimism, but you said the tools are still conservative about beneficial skew overall.
Yeah. Yes. Despite adjustments like CPPR, the core philosophy remains. The tools often deliberately truncate or minimize the beneficial component of skew during the critical timing checks. For example, when checking setup, even if there's positive skew that technically helps, the tool might effectively reduce or ignore some of that benefit in its calculations.
Why do you?
To force the designer to achieve timing closure through fundamentally sound methods, namely, creating short, fast logic paths, good architecture like pipelining, and ensuring low absolute skew through proper clock network design. It discourages reliance on lucky routing.
So what's the practical takeaway for the listener here? What should they focus on?
The big takeaway is, don't rely on random beneficial skew to save your design. Focus on minimizing the absolute clock skew across your synchronous domains. How? By using the dedicated, balanced global clock networks, the BUFGs, BUFHs, etc., provided in the FPGA fabric.
Use the special clock routing resources.
Always. If your design only just barely meets timing because of, say, 500 picoseconds of positive skew that just happened to occur due to random placement, that design is fragile. It will likely fail rigorous STA across all PVT corners, and it might fail unpredictably in production silicon when process variations kick in. Designed for low absolute skew using the global clock buffers.
Okay, let's dive specifically into setup violations now. This is the max delay problem. The data is arriving too late at the capture flip-flop. What are the usual suspects, the root causes?
They generally boil down to the design trying to do too much in one clock cycle. So the most common root cause is simply excessive combinational logic depth. You just have too many LETs, too many logic levels chained together between two registers.
The path is just too long and slow.
Exactly. And this gets magnified, of course, when you analyze the path under those slow PVT conditions, high temperature, low voltage, slow process corner, where every gate and wire is at its slowest.
Makes sense.
Another factor can be large negative clock skew. Remember, negative skew, capture clock arriving earlier than launch clock, eats into your available time for the data path. So a path that was maybe marginally okay might suddenly fail if the skew becomes significantly negative.
And the most obvious one.
Setting an unrealistic frequency constraint. Just telling the tool you want to run at 500 megahertz when your logic path inherently needs, say, 3 nanoseconds, which is only 333 millihertz, the tool can't magically make the physics go faster than it can go.
Right. You're asking for the impossible. Okay, so the goal is clear. Speed up the data path or give it more time. What are the most powerful fixes, especially at the RTL level, where the designer has the most architectural control?
The absolute #1 technique, the architectural heavyweight champion for fixing setup violations, is pipelining and register retiming.
Pipelining. We mentioned this briefly. Can you elaborate?
Sure. Instead of trying to do a complex calculation, like, say, a 32-bit multiply, all within one clock cycle, you deliberately break that long combinational path into multiple shorter stages. You insert pipeline registers strategically within the logic path.
So you cut the long path into smaller pieces.
Exactly. Each piece now has a full clock cycle to complete its smaller chunk of work.
Give us a quick example with numbers.
Okay, imagine your target clock period is 5 nanoseconds for a 200 megahertz clock. But you have a critical path with a combinational logic delay of 8 nanoseconds. That's a setup violation, right? You have a minus 3 ends of slack, roughly.
Clearly failing.
Right. Now, if you can insert a pipeline register somewhere roughly in the middle of that 8-inch path, you might break it into, say, 2 stages, each taking about 4 nanoseconds.
And 4 ends is less than the 5 ends clock period.
Exactly. Both of the new, shorter stages now easily meet the 5 ends timing requirement. You fixed the setup violation. The trade-off, of course, is latency. It now takes 2 clock cycles for the result of that operation to emerge instead of 1.
But you can run faster.
You can run at your target frequency, yes, and potentially even faster if other paths allow. The key thing about pipelining is that it really needs to be considered early in the architectural design phase. Trying to retrofit pipelines into a complex existing state machine or data path can be really difficult and error-prone.
Plan ahead for pipelining. What else can we do at the RTL level, besides adding registers? Can we make the existing logic faster?
Yes, definitely, through careful logic optimization or restructuring. The goal here is to reduce the number of sequential logic levels that the signal has to ripple through.
Fewer steps in the calculation.
Fewer steps, effectively. A classic example comes up with designing finite state machines, FSMs. If you use the standard binary encoding for your states, like state 0, 0, 0, 0, 1, 10, 11, the logic needed to figure out the next state based on the current state, and inputs can sometimes become quite complex. It might involve several levels of gates or LUTs, creating a slow critical path, especially for large FSMs.
Okay, what's the alternative for FSMs?
A very common optimization is to switch to one-hot encoding. In one-hot, each state is represented by a single, unique flip-flop being asserted, while all others are zero.
So for 4 states, you use 4 flip-flops instead of 2.
Exactly. It uses more flip-flops, which seems counterintuitive for area, but the huge advantage is in the next state decoding logic. Because you only need to check if one specific bit is active to know the current state, the logic to determine the next state often becomes much, much simpler, frequently collapsing down to just a single level of logic, like a simple A and D or OR gate.
Ah, simpler logic means faster logic.
Significantly faster, often. This reduction in combinational delay on the critical state transition path can make a huge difference for meeting timing in high-speed FSMs. Other RTL techniques include things like manually restructuring arithmetic operations or maybe choosing different algorithm implementations that have shallower logic depth.
Okay, let's say we've done our best at the RTL level, but we still have some setup violations, maybe smaller ones. What can we do during the implementation stages, placement and routing, or with physical optimizations?
Well, the simplest but often least desirable fix is still clock frequency adjustment. Just slow down the clock. Increase TCLK. If you have 0.2n slack, reducing the frequency slightly might give you that extra 0.2 ns. But, as we said, you sacrifice system throughput, which usually isn't ideal.
Right, that's usually the last resort. What's a more targeted approach?
A more surgical technique is leveraging useful skew. We talked about how positive skew helps setup. The place and route tools, often working with the clock management tiles, MMCM SPLLs, can be guided to strategically and precisely introduce a small amount of positive skew on critical paths.
How to do that?
They can slightly advance the clock reaching the launch flop or slightly delay the clock reaching the capture flop using the fine-grained delay adjustments available in the MMCMs or dedicated clock routing structures. This effectively maximizes the setup time window for that specific path, borrowing a bit of time from the next cycle in a controlled, modeled way.
So unlike random skew, this is intentional and analyzed by STA.
Exactly. Useful skew, when implemented deliberately via clock tree synthesis, CTS planning, and precise clock manager settings, is controlled, understood, and properly accounted for in the timing analysis across PVT corners. That makes it a robust technique for fixing marginal setup issues.
Okay. What if the problem isn't just the clock skew, but the physical distance the signal has to travel?
That's where floor planning comes in. If STA reports show that your worst setup violations, your worst negative slack or WNS paths, involve signals traveling long distances between registers placed far apart on the chip, then the designer needs to step in and provide placement guidance.
Using tools like Vivado Plan Ahead or Cordis Chip Planner.
Yep. You essentially draw regions or boxes on the chip layout view and constrain critical logic modules or groups of related registers to be placed physically close together within those regions.
Keep the critical stuff tightly packed.
Right. This minimizes the routing delays on those critical beta paths. It also helps reduce routing congestion in those areas, which can otherwise force signals onto longer, more roundabout routes, hurting timing. Floor planning is crucial for large, complex designs.
Okay, one last scenario. You run placement and routing, it took hours, and you come back to find a tiny marginal setup violation, maybe negative slack, of just like 0.150 nanoseconds.
Yeah.
Do you really have to go all the way back and rerun the whole process?
Hopefully not. This is exactly where post-route optimization techniques are designed to help. After the main global routing is done, you can run specific commands like VSOP design in the Vivado flow that perform small, localized, incremental optimizations.
What kind of things does it do?
It might try swapping a LUT instance on the critical path for a slightly faster version if one is available nearby. It might replicate a high fan-out driver cell to reduce load. It might slightly reroute just a single wire segment on that critical path to shorten it by a few picoseconds.
Tiny tweaks.
Tiny, targeted tweaks. The goal is to resolve these small, marginal negative slack violations without requiring a full, disruptive, and very time-consuming replacement and rerouting of the entire design. This kind of post-route touch-up is a standard, essential part of the iterative timing closure methodology, especially in those final stages.
Okay.
All right, let's switch gears completely now and go back to the other side of the coin. Hold violations. Remember, this is the minimum delay problem. Structurally more dangerous because slowing down the clock doesn't fix it.
Right. Independent of frequency, data changing too soon after the clock edge.
Exactly. Hold violations happen when the data path delay is too small, allowing the new data launched by a clock edge to arrive at the capture register's D input before the required hold time for the previous data has actually expired.
And this problem gets worse under which conditions?
It's magnified at the fast PVT corner. Low temperature, high voltage, fast process silicon. That's when all the path delays are at their absolute minimum, making it easier for signals to race through too quickly.
Okay. What's the primary architectural reason for hold violations, typically?
Again, it often comes back to clock distribution. Specifically, large positive clock skew is a major culprit.
Wait, positive skew. Didn't we say that helps set up?
It does help set up, but remember, it's a double-edged sword. Positive skew means the capture clock arrives later than the launch clock. For the hold check, which is relative to the launch edge, this late arrival of the capture clock severely compresses the effective hold time window.
Ah, okay. The launch happens, the data starts moving, but the capture clock is late, so the data has less time to remain stable before that late capture edge hits.
Well, put slightly differently, the launch happens, the data races across a potentially very short path and arrives at the capture D pin. But because the capture clock is late, positive skew, the previous data might not have been securely held for long enough after the launch edge before this new data blasts in and overwrites it. The required hold window relative to the launch edge gets squeezed.
Got it. Short path plus late capture clock potential hold violation.
Yeah.
What about just bad clocking infrastructure?
That's probably the other major cause, and often points to a more fundamental design error. If you try to use general FPGA fabric resources like regular LUTs or general-purpose routing wires for critical clock functions, you're asking for trouble.
Like building a clock divider out of flip-flops in the fabric.
Exactly that kind of thing. Or just routing a clock signal locally using general routing instead of the dedicated clock networks. Why is this bad? Because those general fabric resources have unpredictable variable delays. Their timing is affected by nearby logic switching, crosstalk, routing congestion, temperature gradients across the chip, power supply noise.
All sorts of random factors.
All sorts of random factors that introduce uncontrollable, unpredictable skew and jitter onto your clock signal. And the clock needs rock-solid, predictable, sub-nanosecond precision, especially to meet those tiny hold time requirements. Using fabric logic for clocks makes it impossible to guarantee that precision.
Okay, so if you see hold violations cropping up, especially widespread ones, it might signal a basic clocking architecture problem, which means the fix starts with a hard and fast rule.
Absolutely. Rule number 1, mandatory clock management discipline. All synchronous registers in your design must be driven by clocks that have been distributed using the dedicated global clock resources, the BUFGs. BUFHs, BUFRs, whatever your FPGA vendor calls them.
The special low skew networks.
Yes. These are specifically engineered with balanced routing trees, careful buffering, and shielding to ensure very low predictable skew across the entire chip, or at least across large regions. And furthermore, any clock modification like frequency division, multiplication, or phase shifting must be done inside the dedicated clock management tiles, CMTs, like the MMCMs or PLLs. Never, ever try to do it using flip-flops or logic gates in the general fabric.
If you violate that rule, you're likely doomed on hold times.
Very likely, yes. Discovering hold violations late in the design cycle often points back to a violation of this fundamental clocking principle somewhere in the design. It usually requires a significant architectural fix.
Okay, assuming the clocking is architecturally sound using BUFGs and MMCMs, but you still have a specific path failing hold because the data path itself is just too fast. What's the direct fix?
If the data is arriving too early, the fix has to be physical. We need to intentionally slow down that specific data path slightly.
Add delay.
Exactly. The core intervention is adding intentional delay. The tools can often be guided to insert small, low-load buffer elements into that critical data path. Or sometimes they can use slightly longer routing paths. The goal is just to marginally increase the minimum propagation delay of that path just enough to meet the hold requirement.
Sounds simple enough, just add a buffer. But
Yeah.
there's a catch?
There's always a catch. This is the classic dual constraint dilemma. When you add delay to fix a hold violation,
You risk creating a setup violation.
exactly, you have to immediately recheck the setup timing for that same pass. You need to add just enough delay to fix the hold problem without adding so much delay that the data now arrives too late for the setup check.
That sounds like a really delicate balancing act.
It can be incredibly delicate. We're often talking about adding delay on the order of tens or maybe a few hundreds of picoseconds. It requires very precise control and careful analysis by the SDA tools. Sometimes the tools can handle this automatically during post-route optimization, but other times it might require manual intervention or constraints.
Okay, let's circle back to the MMCMs and PLLs. You said they're crucial for deskewing the clock. How do they actually achieve that? How do they manage to make the clock arriving deep inside the chip align so perfectly with the clock coming in from the outside?
It's a really clever mechanism, usually involving a delay-locked loop DLL or a locked loop PLL circuit inside the MMCM block. Let's think about a DLL for deskewing. It takes the reference clock signal coming into the FPGA from an external pin.
The input clock.
Right. It then generates the internal clock and distributes it out onto the global clock network, like a BUFG. But here's the key. It also takes a version of that distributed clock back into the MMCM via a dedicated feedback path.
It looks at its own output after it's gone through the network.
Exactly. Inside the MMCM, it compares the phase of the original input reference clock to the phase of this feedback clock that has traversed the internal clock network. Now, inevitably, the feedback clock will be delayed compared to the input clock because it took time to travel through the BUFG and the routing tree.
There's always some positive delay.
Always some positive delay. The MMCM measures this phase difference, this delay. Then it uses a digitally controlled delay line on its output to introduce a precise amount of negative delay, or phase shift, essentially, a phase advance to the clock it sends out.
It makes the output clock start earlier to compensate for the network delay.
Precisely. It adjusts the phase advance until the clock arriving back on the feedback path is perfectly phase aligned with the original input reference clock. The net effect is that the clock edge arriving at the actual clock pins of all the flip-flops connected to that BUFG network is synchronized with near zero skew relative to the clock edge arriving at the boundary of the FPGA.
That's pretty sophisticated. It actively cancels out the distribution delay.
It actively cancels it out. This is absolutely paramount for ensuring hold time stability, especially for interfaces where the FPGA is receiving data synchronously from an external chip clocked by the same source. You need that edge alignment to be perfect.
One last point on architecture and hold times. You mentioned earlier that paths clocked on the same active edge, like rising edge launch to rising edge capture, are the most sensitive to positive skew and hold violations. Why is that again?
Because the entire timing relationship launch, propagate, setup, hold has to happen within the confines of a single clock period relative to that single edge type. Any positive skew directly eats into the already tight hold margin related to that launching edge.
Okay. Are there architectures that are naturally less sensitive?
Yes.
Yeah.
If you can design paths that operate between different active edges, for example, data launched on a rising edge but captured on the next falling edge, or vice versa, you often get significantly more timing margin inherently. Because the effective time window for the data to propagate and settle is naturally larger, often closer to half a clock period, rather than being tightly constrained around a single edge. This built-in extra margin makes these kinds of dual edge or opposite edge clocked paths naturally less susceptible to marginal hold time errors caused by small amounts of skew. Sometimes you can leverage this architecturally if hold timing is proving particularly difficult on same edge paths. Okay, moving beyond the basic setup and hold fixes, let's talk about some more advanced timing techniques, especially using those powerful MMCM or PLL blocks. We mentioned deskewing, but they can do more, like fine phase adjustment.
Right, you mentioned this helps with margin balancing. How exactly does shifting the clock phase help meet both setup and hold margins at the same time?
Okay, let's take a typical scenario. After initial place and route, maybe STA reports that you have a comfortable 500 picoseconds of positive setup slack on a critical path, but you only have a tiny 50 picoseconds of positive hold slack on that same path.
So you're great on setup, but really marginal, almost failing on hold.
Exactly. The design is unbalanced. Now, you can go into the MMCM configuration and tell it to introduce a small, precise, positive phase shift to the clock feeding the capture flop for that path. Let's say you advance the capture clock by 100 picoseconds.
Making the capture clock arrive 100 Ps earlier.
Right. What does this do to setup? It makes the setup requirement tighter by 100 Ps because the capture edge comes sooner. So your setup slack decreases from 500 Ps down to 400 Ps.
Still plenty of margin there.
Still plenty. But what does it do to hold? Remember, the hold check is also relative to the capture edge. By making the capture edge arrive 100 Ps earlier, you've effectively given the data an extra 100 Ps to meet the hold requirement after the launch edge.
So advancing the capture clock helps hold time.
It does. So that 100 Ps phase advance reduces setup slack but increases hold slack. Our original 50 Ps hold slack now becomes 150 Ps.
So you went from setup 500, hold 50 to setup 400, hold 150. Much more balanced.
Exactly. You've traded some of your excessive setup margin to buy more hold margin, making the path more robust overall. This fine-tuning capability of the MMCM phase shift is crucial for pushing performance while maintaining reliability across all corners. You strategically balance the margins until both setup and hold have acceptable positive slack.
That's really powerful. You also mentioned phase shifting, helps with electrical stability. Something about noise.
Yes, noise mitigation, specifically dealing with simultaneous switching output, SSO noise, or just general simultaneous switching noise, SSN, within the chip.
What causes that?
When you have thousands or millions of flip-flops and logic gates, all switching state at the exact same instant triggered by the same clock edge, they all draw a large amount of current from the power supply rails simultaneously. This huge instantaneous current demand causes a temporary voltage drop, or droop, on the power and ground planes.
Like a mini brownout inside the chip.
Kind of, yeah. These voltage fluctuations are noise. They effectively reduce the voltage levels seen by the transistors, which can eat into your timing margins and potentially cause functional failures if the noise is bad enough.
So how does phase shifting help?
By using the MMCM to introduce slight phase differences between the clocks feeding different major blocks or regions of your FPGA design, you can stagger the switching times. Instead of everyone switching at T0, maybe block A switches at T0, block B at T plus 50 Ps, block C at T plus 100 Ps, and so on.
Spread out the current draw over time.
Precisely. You distribute the peak instantaneous current demand across a slightly wider time window. This reduces the magnitude of those SSO spikes and helps maintain better power integrity, which in turn preserves your timing margins and improves overall system stability, especially in very high-speed, dense designs.
Clever. Okay, let's shift focus to the boundaries of the FPGA, interfacing with the outside world. You stress that defining timing constraints for I/O interfaces using SDC is absolutely mandatory. Why can't the tool just figure it out?
Because the FPGA timing engine's world ends at the pins of the chip. It knows everything about the delays inside the silicon, the LUT delays, the routing delays, the flip-flop characteristics, but it has absolutely no inherent knowledge of what's connected externally.
It doesn't know about the other chips or the PCB traces.
Exactly. It doesn't know the clock-to-output delay of the external memory chip sending data to the FPGA. It doesn't know the propagation delay of the signal traveling along the printed circuit board, PCB trace. It doesn't know the setup or hold time requirements of the external chip that's receiving data from the FPGA.
So without constraints, it's flying blind at the edges.
Completely blind. If you don't provide accurate I/O timing constraints in your SDC file, the STA tool typically assumes zero delay outside the chip, which is obviously wrong, and leads to functionally meaningless timing analysis for all your interfaces. You must mathematically model the timing characteristics of the entire external system connected to your FPGA pins.
Okay, let's take a concrete example. An input path, where the FPGA is capturing data launched by some external chip. You use the set input delay command in SDC. What do the max and min options represent?
Right, set input delay tells the STA tool about the delay of the data arriving at the FPGA input pin relative to the clock edge at that pin. You need two values to define the arrival window: NAS max and AS min.
What is NAF's model?
The NAX constraint models the longest possible time it takes for data to arrive at the FPGA pin after the clock edge that launched it externally. This calculation must include the external chip's maximum clock-to-output delay, often written as TC2 max, plus the maximum delay of the signal traveling across the PCB trace.
Longest chip delay plus longest board delay.
Yep. That total maximum external delay value you provide with NAX is what drives the internal setup check for that input path inside the FPGA. You're essentially telling the FPGA timing analyzer, be prepared, the data might arrive this late relative to the clock.
Okay, and the ASMIN constraint.
The Dunin constraint models the shortest possible time it takes for data to arrive at the FPGA pin after the launching clock edge. So this calculation needs the external chip's minimum clock-to-output delay, TC2Q, plus the minimum delay of the PCB trace.
Shortest chip delay plus shortest board delay.
Right. This total minimum external delay provided with the bin drives the internal hold check for that input path. You're telling the analyzer, watch out, the data might change this early relative to the clock. Together, NectaMax and NiKedamin define the complete timing window the FPGA's input capture logic must successfully operate within.
So the SDC constraints define the requirement. What about those special I/O primitives like I/O delay or I delay, O delay? What's their role?
They are the physical adjustment mechanisms. Think of them as tiny, digitally controllable delay lines located right inside the I/O buffer, the IOB itself, very close to the physical pin.
So they add real physical delay.
Yes, they can add very fine-grained, precise amounts of physical delay, often configurable in steps of just tens of picoseconds, like maybe 50 or 78 picoseconds per tap, depending on the device. Once your SDC constraints, set input delay, set output delay, have mathematically defined the required timing relationship at the pin, the place and route tools, or sometimes the designer manually, will use the I/O delay primitive to physically tune the arrival or departure time of the actual data signal right at the pin.
Shifting the signal edge slightly to meet the SDC requirement?
Exactly. They shift the edge until it perfectly aligns with the timing window dictated by the constraints, ensuring the internal setup and hold checks pass. So the I/O delays are the implementation mechanism used to meet the requirements defined by the SDC constraints. They are not a substitute for having accurate constraints in the first place.
Got it. Constraints define the target. I/O delay helps hit the target. What about controlling timing on purely internal paths that might not follow the standard single-cycle assumption? You mentioned false paths and multi-cycle paths.
Right. Sometimes the default SDA assumption that data launched on one clock edge must arrive before the next immediate clock edge isn't logically correct for certain paths.
Like paths between different unrelated clock domains.
That's a prime example for false paths. If you have two clock domains that are completely asynchronous and you've already put in proper CDC synchronizers, like the two flip-flop synchronizer we discussed, then trying to do a timing analysis on the combinational path between those two domains is meaningless. It will likely fail timing, but it doesn't matter because the synchronizer handles the timing uncertainty.
So you tell SDA to just ignore it.
Exactly. You use a set false path constraint to explicitly tell the SDA tool, don't bother analyzing the timing on this specific path or between these clock domains. This can significantly speed up compilation time by pruning unnecessary analysis. But, and this is a huge warning, you must never use set false path simply to hide or ignore a genuine synchronous timing violation that you don't know how to fix. That's just sweeping a real problem under the rug. Use it only for paths that are truly asynchronous or logically irrelevant to timing.
Okay. What about multi-cycle paths?
Yeah.
Set multi-cycle path. When do you need those?
You use these when you have a specific synchronous path where the logic is intentionally designed to take more than one clock cycle to complete.
Like that complex arithmetic unit example.
Perfect example. Maybe you have a pipelined multiplier that takes, say, 4 clock cycles, N4, for the result to be valid at the output registers after the inputs are latched. By default, STA assumes N1. It will try to time the path as if the result needs to be ready in just one cycle, which will obviously fail massively.
So you tell STA it's allowed to take 4 cycles.
Correct. You apply a constraint, like set multi-cycle path for setup to the path. This tells SDA to relax the setup check. Instead of requiring the data to arrive before the capture clock edge at time $2.1ers, it shifts the requirement out to the capture clock edge at time 2.7. It gives the path the 4 full clock periods it logically needs.
That makes sense for setup, but you hinted earlier this can mess up the hold check.
It introduces a critical complexity for the hold check, yes. Remember, the hold check is normally done relative to the launching edge, $T in this case, to ensure data doesn't change too quickly and get captured incorrectly by the next edge, $1.
Right.
When you apply a multi-cycle setup constraint, say set multi-cycle path 4 setup, you've told the tool the data doesn't need to arrive until edge $4. The tool might now think, great, I have tons of setup slack, I can optimize this path like crazy, maybe make it super fast.
Uh-oh.
Oh, it was right. If the tool makes the path too fast, the data launched at $T might actually arrive and stabilize before edge $1. If the hold check hasn't also been adjusted, the tool might not see a problem. But functionally, the capture register at the end might incorrectly latch this new data on edge $1 instead of waiting for edge T-Torta-Wars.
So the multi-cycle setup constraint needs a corresponding multi-cycle hold constraint.
Absolutely. You need to tell STA how to adjust the hold check as well. The standard practice is usually to constrain the hold check relative to the edge before the intended capture edge. So if setup is multi-cycle N, capture at $2, You typically apply a multi-cycle hold constraint of N1. In our N4 example, you'd add set multi-cycle path 3 hold.
What does set multi-cycle path 3 hold do?
It tells STA to perform the hold check relative to the 333I clock edge. This ensures that the data launched at $2 remains stable and doesn't change until after edge $233, preventing it from being accidentally captured too early on edges T21, $2.2, or 233. It keeps the data stable until just before the intended capture edge $234. Getting these multi-cycle hold constraints wrong is a very common and tricky source of errors in complex designs.
Okay, so I've got the theory, the physics, the architectural fixes, the constraints. Now we need the actual process. Time enclosure isn't usually a one-shot deal, right? Our sources often call it an iterative art, something that requires real designer diligence, not just pushing buttons on the tools.
That's absolutely true. You can't just write some RTL, throw constraints at it, hit compile, and expect perfect timing, especially on complex high-speed designs. It requires a systematic, iterative approach. Flows like the Zelling's ultrafast design methodology try to formalize this.
So what does that iterative process look like? Where do you start?
It really starts before you even run synthesis, with initial design checks, sanity checks. First, double-check your clocking circuitry. Are all clocks generated and distributed correctly using MMCM SPLLs and global buffers? Are the frequencies reasonable? Second, look at resource utilization estimates. If your design is already using, say, 90% or more of the FPGAs, LUTs, or register,
You're going to have routing problems.
you're almost guaranteed to have massive routing congestion, which makes time enclosure incredibly difficult, if not impossible. You might need a bigger chip or need to optimize the design for area first. And third, do a quick back-of-the-envelope check. Does your target frequency even seem physically realistic given the estimated depth of your longest logic paths? Sometimes designers aim too high from the start.
Okay, initial sanity checks passed. You run synthesis, then place and route, and inevitably you get timing violations. What's the next step in the iteration?
You need to establish a baseline and track progress. This is timing baselining. It means you meticulously review the timing reports generated after each major stage: synthesis, placement, and routing. You look at the key metrics: worst negative slack, WNS, total negative slack, TNS, the number of failing endpoints.
And you track how these change.
Exactly. You track the quality of results, or QOR. For instance, if your WNS is okay after placement but gets much worse after routing, what does that tell you?
The problem is likely routing congestion. The router couldn't find short paths.
Precisely. But if your WNS is already terrible right after synthesis, before physical placement even happens,
Then the problem is likely architectural. The logic paths are just too deep in the RTL itself.
right. This baselining and tracking helps you pinpoint where in the flow the timing problems are originating or getting significantly worse.
Which leads directly into the next crucial step: root cause analysis, RCA. Really digging into why a specific path is failing.
Yeah, you can't just randomly try fixes. You need to rigorously analyze the failing path reported by STA. Is it failing setup, max delay, or hold, min delay? Look at the detailed path report.
What do you look for in the report?
How many logic levels are there? Is the delay dominated by logic or by routing? Where are the start point and end point registers physically located on the chip? What's the clock skew on this path? Is it positive or negative? Are the constraints for this path correct?
So you're trying to determine if it's an RTL architectural flaw, needs pipelining, an incorrect constraint issue, or a physical implementation problem like skew or congestion.
Exactly. You have to diagnose the root cause accurately before you can apply the right fix. Trying to fix a congestion problem by changing RTL won't help, and trying to fix an overly deep logic path with floor planning alone is unlikely to succeed. RCA is critical.
Now, one interesting point our sources raised is this idea of the non-convergence struggle. The tools try to fix the worst path, but sometimes they seem to get stuck.
Yes, this is a common frustration. It's like a local optimum trap. The Place and Route tool's optimization engine typically focuses on the path with the absolute worst negative slack, WNS. It'll try various things: moving cells, changing routing, maybe replicating drivers to improve the timing of that specific path.
Which sounds good.
It sounds good, but the changes it makes to fix that one path might inadvertently have a negative impact on other paths that were previously needing timing, perhaps only marginally. So, the WNS might improve slightly in one iteration, but the total negative slack, TNS, the sum of all negative slacks across all failing paths, might stay stubbornly high or even increase a bit.
The tool fixes one problem but creates another elsewhere.
Essentially, yes. It can get stuck in this loop, making small local improvements to the WNS path, but failing to reach a global solution where all paths meet timing. The optimizer keeps circling around this local minimum without finding the overall best placement and routing solution.
So when the automated tools get stuck in this non-convergence loop, what's the escape route? How does the designer intervene?
This is where active designer guidance becomes absolutely essential. You have to step in and provide stronger hints or constraints to the tools to break them out of that loop. This often involves things like,
Like floor planning?
yes, defining more specific physical constraints, using floor planning regions, P-blocks, to manually group related logic, maybe even locking down the placement of certain critical registers. You might need to apply specific physical optimization directives to certain hierarchies. Or sometimes you might need to adjust the tool's optimization strategy settings.
You're essentially giving the tool a nudge in a different direction.
A nudge, or sometimes a firm push. You're using your understanding of the design structure and the timing reports to guide the tool towards a better area of the solution space that its automated algorithms couldn't find on their own. Breaking these convergence struggles often requires significant designer expertise and experimentation.
Okay, so after potentially many iterations of analysis, fixing, constraining, and guiding the tools, you finally achieve it. Zero negative slack. WNS is positive. The design needs timing. Is the job finally done? Can you ship it?
Absolutely not. This is perhaps one of the most critical points for real-world reliable hardware. Achieving zero negative slack is necessary, but it is not sufficient for robust, production-ready design.
Why not? If it meets the timing requirements in the tool, shouldn't it work?
Because the timing models used by the STA tool, even with all the PVT corner analysis, are still just models. They are very sophisticated statistical models, but they cannot capture every possible real-world nuance and variation.
What kind of things are missing?
Things like minor manufacturing variations from wafer to wafer or even die to die that fall within spec but might slightly alter delays. The effects of aging on silicon over years of operation. Power supply noise fluctuations that might be slightly different or worse than what was modeled. Temperature gradients across the chip that might not perfectly match the uniform temperature assumed in the corner analysis. The inherent statistical nature of the delay models themselves, they represent typical or worst-case behavior, but there's always some distribution.
So zero slack means you're right on the edge, with no safety margin for any of that real-world messiness.
Precisely. Zero slack is functionally equivalent to failure when you consider mass production and long-term reliability. If your design just barely meets timing in the idealized world of the STA tool, it's highly likely that some percentage of manufactured chips will fail in the field under certain conditions due to these unmodeled effects.
So what's the real final goal then?
The real goal, the target for any industrially robust design, is to achieve significant positive timing margin. You don't just want zero negative slack. You want all paths to have a healthy amount of positive slack.
How much positive slack are we talking about?
Industry best practices, as reflected in our source materials and flows like ultrafast, often recommend targeting something like 10% to 15% positive slack on your critical paths relative to the clock period after accounting for all uncertainties. This buffer provides the necessary margin to absorb those real-world variations and ensure reliable operation across the entire product lifetime and manufacturing spread. Zero slack designs are simply too risky for production.
Okay, so wrapping up this deep dive into the world of FPGA timing, if we boil it down, reliable high-speed design really seems to rest on three crucial pillars.
Lay them out for us.
First, at the architectural level, a highly pipelined RTL architecture. This is your primary weapon against setup violations, that max delay problem. Break down long paths.
Got it. Pillar 1, pipeline the RTL. Second, meticulous clock management, using dedicated MMC-MPLL clocking resources and global buffer networks. This is absolutely essential for robust, deskewing, precise phase adjustment and ultimately conquering those tricky minimum delay hold violations.
Pillar 2, pristine clocking infrastructure.
And third, accurate SDC I/O modeling. You have to use constraints to mathematically bridge that timing gap between the precisely defined internal world of the FPGA silicon and the often messy, variable external world of PCBs, connectors, and other components.
Pillar 3, constraint the boundaries properly. Pipelining, clocking, constraints.
You nail those three, and you're well on your way to robust timing closure.
All right, so let's leave you, our listener, with a final, maybe slightly provocative thought to chew on. We spent a lot of time emphasizing how hold violations are, in a sense, structurally more critical than setup violations. Why? because you can't just fix them by slowing the system down.
Right. They point to fundamental issues in path delay or clock skew.
Exactly. They're an intrinsic problem related to minimum path delays and the integrity of the clock infrastructure itself, often made worse by skew. So this implies that the ultimate reliability of a high-speed digital system might be defined less by how much raw computation, how much logic you can cram into a single clock cycle that's the setup problem, pure speed, and more by the sheer integrity, precision, and management of the clock distribution network itself, the hold problem, the infrastructure.
That's an interesting way to frame it. Reliability hinges on the plumbing as much as, or maybe more than, the engine speed.
Yeah. So the provocative thought is, what other areas of highly complex engineering out there, maybe you think about massive distributed systems like global sensor arrays, continent-spanning power grids, or huge cloud data centers are similarly limited or defined not necessarily by the raw processing power of their individual nodes, but more fundamentally by the integrity, latency, and synchronization of the underlying infrastructure that connects them all. Where else is the plumbing the ultimate bottleneck for reliability and performance?
That's a great question. Lots to think about there in terms of coordination versus computation.
Definitely something to mull over. We hope this deep dive into FPGA timing has been illuminating. Join us next time for another deep dive.